Okay, so this is the step response of 1 over s plus 1, as we have seen. It's a monotonous response. It has a steady state gain of 1. The response is unit step response, so the input is 1 here. Let me briefly show you how we did it again. So we go to Octave again. We load the control package by pkg load control. Then you enter the transfer function by entering the numerator and the denominator of the system. So it is, your system is 1 over s plus 1. When you say step, you get the step response of the system. But if this response is too small, let's say, you can say something like step of g for a time amount of 10, let's say, in which case you will be seeing the step response up to time 10. But I have to share it with you each time. So the step response, as you see, is up to time 10 here. And another thing you can notice is approximately, I'm sorry, in 4 or 5 time constants, you can say 4 or 5, the response gets to the steady state value. This is the steady state value is 1, as you see. 4 time constants is the usual thing. I think you get to 98% of the response. Maybe in 5 time constants, you get to like 99% of the response. So, this is a first order system step response. We can say, for example, the impulse response of, what is this? Something very strange happened. Anyway, let me close this. Let me start it again. Okay, let's share it again. Okay, so G is, let's say, we said transfer function of 1 and 1, 1. And then we said step, we found it, but let's find the impulse response. And that is obtained by impulse command, impulse of G. Let me show it to you. So this is the impulse response. It starts from here. The impulse you suddenly put on the system acts like an initial condition, and then it goes to 0. It is an exponential decay, exactly an exponential decay. So this is the first order system response. Let's go to a second order system now. G is equal to, let's say, you don't have to say G, you can use H, T, whatever you like. G is equal to transfer function of, let's say, we say 5, and then the denominator is 1, 1, and 1. So it is s squared plus s plus 1. So the pole, if I say pole, for example, of G, I find that the poles of G are at minus 0.5 plus minus 0.866 I or J. They are complex conjugates. This system has oscillatory response. For example, the step of G, if I say this, we will find that the response is like this. The response is oscillatory. You can, and the steady state value to a unit step response, as you see, is 5. We have reached the 5 value here. So the system, second order system responds as such. And everything depends on the natural frequency. Well, the way the system responds depends on the natural frequency and the damping ratio. For example, I can change this system. Let's say instead of 1, 1, 1, I can use, for example, 1, 2, 1, which will be a critically damped system. If I I didn't change the okay, but so I have changed this thing to, as you see from here, 1, 2, 1. This is a which means s plus 1 squared. So its damping ratio is 1 here. If I find the step response of, let's say, up to time equals 10, let me show what we get. We get a second order system, second order critically damped system response. It has no oscillations, as you see. There are no oscillations here because the damping ratio zeta is 1 here. Okay.
Hujam, you might not have to change the screen again and again because I think you're just sharing the application. So if you share your screen, you won't have to like change again and again. So if you can try that, that might help you.
Well, I'm sharing the application, but it opens 2 different screens. So I couldn't find a way to do anything else. How do I do it?
Hujam, in the share screen option, you might have you're probably choosing Octave, and then when you're going for the figures, you're just choosing the figure application. So if you just share the screen, that will be easy for you. Like when the graph is plotted, you can see both of them on the same screen because you didn't have issues in the recording, and in the recording everything was smooth.
I didn't get what you have said, but let me try.
Hocam share screen yaptığımız zaman orada direkt screen paylaş diye bir şey var. Screen. Uygulama değil, direkt screen olarak çıkan bir şey var. Ona basarsanız bütün ekrana paylaştığı için sürekli değiştirmenize gerek kalmaz.
Screen. Okay. Actually, I didn't know. Probably it shares everything you have here, right?
Yes, hocam.
Like this. So you see my desktop now in that case, right?
Yes, hocam.
Okay, that's a good idea. Thank you. Actually, I didn't know that. I should have known, but I don't. Okay, so you see it now, right? This is the Octave screen and this is the float. It is okay, right?
Yes, hocam.
Yes, hocam.
Okay, thank you. We don't lose time by this. So this is why did we get this? I have no idea. Okay, we have a critically damped system response. Its steady state gain is 5, and it settles about in, I don't know, 8 seconds or something. We can change this. For example, we can have 1, 0, 1, which is s squared. Let's say this is 1 over s squared plus 1. This is an undamped system. If you look at the step response of this system now, this is what we get. Or let's increase this a little bit. Let's say we increase it up to 50. The response will be like this. You see that the response is between 0 and 2. Steady state is 1, but it never reaches that because it's oscillatory, purely oscillatory, the response. And the period of oscillations is something like, I don't know, let's say it is 6 seconds or something. And that is 2 pi over omega n. 2 pi is 6.28. Omega n, as you see, is here is 1. So it is, period is like 6.28 seconds, as you see. Period of oscillations. Okay, if you increase the damping a little bit, like 0. Let's say 5, you have some damping in the system, and let's look at the poles of this system. As you see, the poles are complex conjugate. Now, if we look at the step response, you will see that actually we don't have to have it that much. We can have it like 20 or something. The response is underdamped. So this is the second order system response, as we see. Okay. Let's keep this for the time being. We will continue with this, but well, we looked at first order systems, second order systems. Well, there are other kind of systems as well, but first and second order systems are very typical. That is, the parameters we have in them are commonly used, so we will be we have studied them in detail. Well, you know, we can go on like this third order, fourth order systems, but we don't do this. But there is something we have to talk a little bit about. Again, I am sharing this, right? I'm sharing the Microsoft whiteboard, I suppose.
Yes, Ajahn.
Yes.
Yes, but then the pen doesn't work as usual. Okay. Now remember that we call the if you have a transfer function g of s, which is the numerator divided by the denominator. This could be factored as the poles, let's say, and then you could have zeros. But in these systems we didn't really have zeros. Zeros are kind of important, not as important as the poles of the system, but they also have the zeros of a system are important. They affect the transient response, and some systems have zeros. Some systems have, let's say, zeros. The output of such systems depends not only on, let's say, input U, but also to its derivatives, let's say. Now, what do I mean by this? I mean the following. For example, if you have such a system, a mass spring damper system again, I think this was a B. Let's call this input U, and the output is Y. So U is the displacement input given to your spring and damper. The equation of motion of this system is going to be my double dot plus Py dot plus Ky equals Pu dot plus Ku. As you see, the transfer function G of S, which is output over the input, Ds plus K, so that the system has a zero at you equate Bs equals K to 0, S equals minus K over D. Now, the zeros influence the system response, but they don't make the system stable or unstable. You can have all sorts of systems with zeros, and actually they can affect the response quite drastically. So let me try to show a few examples using the octave. Let's say, share screen. Okay. Okay, you see the octave now, right? Yes?
Yes, John.
Okay. Let's put a 0 on our system now. Let's say this is our system. Let's say this is a 1, 1. And let's say instead of this, we have 1 and 1, let's say, so that the system has a 0 at 1 now. So if you say 0 of G, for example, you are going to get 0 at minus 1, and pole of G is this. So if you look at the step response, now the step of G will be kind of different. Well, it doesn't look too different, but let's compare it with, let's say, let's have it compare it with the following one. Let's say this is G, and let's say that this is G1. Okay. So I don't know if I can do this, but step of so as you see, I think yes, G is the one without the zeros. The blue one is without the zero, and G1 is with the zero. And you see that it has a drastic influence on the system response. Well, not drastic, but it has an influence. It's not the same response anymore. The steady state is somehow the same here, but the response is different. Actually, the control design is affected by the zeros. It's not trivial, but as I have said, it's not as important as the poles of the system. And if you change the zero of the system, for example, instead of 1, 1, if you make it, let's say, 1, what should I have? Let's say 0.2 or something. I think this will have a more influence. Well, it's a bit strange, of course. It has changed the steady state gain, of course, what I did here. But let me do it this way. So that the steady state gain is the same. Yeah, actually, this is very drastic. The blue one is without the zero, and the red one is with the zero. They have the same steady state gain, but the zero makes the system overshoot terribly, as you see. This system has a zero at well, I think at minus 0.2, close to the origin, and those zeros have influence on the step response. So zeros are not to be ignored, but we are not going to be, spending too much time on them for the time being. But just keep in mind that the zeros are important, okay? So, let me just write here that zeros influence the time.
Hocam, sorry for interrupting. Could you please explain what is the difference between the one has zeros and the one that has no zeros in the octet?
Just a second. You want me to explain this figure, for example?
Yes, hocam.
It just comes out that way, though, the physically, it doesn't have too much of an explanation, I suppose. You could, explain it physically. But the one that has zero, the transient response has a very high overshoot, as you see. If you look at the pole zero pattern of these systems, let's say this is real and this is imaginary. Let's say that the poles are complex conjugate. Now, if you have zero of a system, if it's here, for example, it doesn't have much of an influence on the system response. If it gets here, for example, if it's on the order of the zero pole, it has an influence, and this zero here has a lot of influence. That is, the closer the zero gets to the imaginary axis, it has more influence, okay? It has, let's say, little influence. That's high. Keeping the poles constant, let's say, okay? So, well, all these things can be explained in terms of the root locus and so on, but we are not going into the details of those kinds of things. Basically, as the zeros get closer to the imaginary axis, they have more and more influence on the system response. Okay, now.
Hocam,
Yes.
does anything change if the zeros are positive?
Okay, that's a good question. Let's see what changes. Let me give you an example. It does, things change, yes, that's right. Let me go to MATLAB again, and let's make it minus 0.2 here. Now the 0 is, it's on the negative, it's on the left half axis, so that the 0 of this system, G1, where is that? 0 of G1 is at 0.2, not minus 0.2, but plus 0.2. Actually, you will see that it will give you a strange response. First of all, the steady state gain has changed now. It has become -1, but let's change that also. Now, okay. Well, there is an overshoot, but overshoot is on the opposite side, as you see. There is an undershoot. This is very drastic, but let me just show it with the following. Let's say that we have a 0 at -1, so that we look at it here. This is more reasonable. This system has a 0 at, the red one has a 0 at +1. Okay. Now the response starts from positive 0, but then goes to negative value. So it undershoots instead of making an overshoot. This is called an inverse response. Okay. The response is in the opposite direction. It is just like the following. You are driving a car, okay? You turn the steering wheel, let's say, towards the right, and then the car turns to left. Actually, at very high speed, this can happen, okay? This is called an inverse response. But it happens for a short while, then it comes back to its original value. So the 0 like this, a negative or a positive 0 causes an inverse response in the system response.
Thank you, John.
Yeah, and also such systems are systems that have inverse response are difficult to control. They are, the control can be limited, but let's not go into that for the time being. Okay, so, and also, as you say, let's put it here. Here you have, if you have a 0 here, this causes, let's say, inverse response, like the step response of the system does the following, okay? So there is a portion of the response that is inverse response. Okay, so let's go to well, as I said, we don't have just first order, second order systems. Okay, we usually have, the system can be of arbitrary order, third order, fifth order, whatever. It can be described by all sorts of equations, and basically the transient response is of such systems equals the sum of transients, let's say, corresponding to poles As you see, the system, in this case, if you have a high order system, you will have poles like, like two of them here, one here, one there, and then you might have zeros like this. This is the real axis. This is the complex plane at which we locate the poles and zeros. Okay. But all the responses are going to be of the form. The transients will contain terms like e to the minus at, t times e to the minus at, if you have multiple poles. You might have e to the minus at cosine omega t, e to the minus at sine omega t, etc. It will be made up of such terms. These a and omega terms are determined from the system parameters. But I want to emphasize the following: the dominant poles approach here. In many systems, although you have high order systems, you can represent the system response by its dominant poles. Let's say that you have a system of this kind. This is the real axis, this is the imaginary axis. Let's say you have two poles here and another set of poles here. Okay. Now, these two poles that are close to the imaginary axis, these will be called the dominant poles. The bunch that are here are less important in the response, okay? Why are they less important? Because they die out rather quickly, whereas these ones go on and die out slowly. So the poles close to j omega axis, poles close to imaginary axis are called dominant poles. They dominate the system response. Let me give you an example using MATLAB. We can, well, let's not close it. Let's define a transfer function now. What should we say? Let's forget about the zero now. Let's select a third order system or something. One. This is a third order system. Let's see how it responds. This is V1, right? It almost responds like a second order system actually. What are its poles? V1. Well, I should say pole, I'm sorry. -1. Okay. So one of the poles is at -1. It should be okay. Let me do it this way. The denominator is equal to I don't know if you will understand this, but
So Hujam, the ones that are down like minus 0.5 are the ones that are closer to the imaginary
Yes, they
axis.
are, but I want them to be even, you know, even far apart. So I want a pole at, let's say, -5 or something. So if a pole is at -5, it is s plus 5, right? So let's say it like this. So yeah, this is the roots of this denominator. I'm sorry, roots. Yes, this is what I want. So this one and the denominator. This is a system whose poles are at these values. So the step response of this G1 is like this. As you see, this is very close to the step response of G, which I will define as follows. G as a second order system, as the transfer function of 1 and 1, 1, 1. Okay? So the step of G and G1 will be kind of, oh, something wrong. What is wrong here? The steady state gain is wrong. What I should do is okay. The steady state of both of them are 0.2 now. Anyway, as you see, the red one is a second order system, and the blue one is a third order system. Well, you know, there is a difference between them, but usually in such systems, if the one of the poles is far apart, you can approximate the response by a second order system response. Okay. If they are even far apart, you can have a better approximation. That is, second order systems you know, play an important role in the system response because they have the dominant poles in the system. These poles are the dominant ones. So let me take a break here if you don't have any questions. Any questions?